Gauss's fundamental theorem of algebra states that a polynomial of degree n has exactly n roots. Let's look at a specific example. Let's say we have f of x is equal to 1 minus x squared. I can look at the graph of f, and I'll have this upside down parabola which has the intercepts x equal minus 1 and x equals 1. This is a polynomial of degree 2, and we have 2 roots. We could look at x minus 1 all squared. That's also a polynomial of degree 2, but here it only has 1 root. The other root is given by the fact that the gradient also is equal to 0 at x equals 1, so it has a multiplicity of 2. If we look at the graph of x squared plus 1, however, there's no real number that we could insert into this equation such that f of x equals 0. No number squared plus 1 will give you 0, not for real numbers. So there seems to be some contradiction between the fundamental theorem of algebra and this quadratic polynomial. It turns out that we need a larger number system. We need to include the square root of minus 1, which we denote by I. So we'll define the complex numbers to be the set of all a plus ib, where a and b are real numbers. So if we look at some specific examples of what a complex number is, we could take z is equal to 1 plus 3i. The part that doesn't have an I in it, the part that has no square root of minus 1, we call the real part. So the real part of this complex number is going to be 1. The part with the I we call the imaginary part. So the imaginary part of this complex number is going to be 3. If we just took the imaginary part to be 0, then we see that the real numbers form a subset of the complex numbers. So any real number such as z equals 1 can be taken to be a complex number also. Okay, so let's look at this first example. Let u equal 1 plus 2i and v equal 3 minus i. We want to find u plus v. So let's write u plus v as 1 plus 2i plus 3 minus i. We will remove the brackets, and now we will just combine the real and imaginary parts. We get u plus v is 4 plus i. Let u be 1 half minus 3i and v be 2 plus 1 half i. And we'll try to find u minus v. So again, we'll write it as 1 half minus 3i minus 2 plus 1 half i, and we'll just remove the brackets again. Now if we combine the imaginary and the real parts together, we have 1 half minus 2, and then minus 3i minus 1 half i. And then if we add that together, we just have minus 3 halves minus 7 halves I. Let's look at a third example now. Let u equal 3 minus 2i and v equal 1 plus 6i. We want to find u times v. So again, write u times v as 3 minus 2i times 1 plus 6i. Then we can expand this as 3 times the first part minus 2i times the second part. And what we'll do is we'll just expand this. 3 plus 18i minus 2i plus 12. And then what we find is that u times v is just 15 plus 6i. Before we can talk about dividing complex numbers, we need to talk about complex conjugates. Given a complex number z a plus ib, we'll define the complex conjugate of z to be the complex number z bar, which we write as a minus ib. So if we were to look at this visually, if we graph z is equal to a plus ib, then the conjugate is going to be given by z is equal to a minus ib, and the conjugate is just taking the reflection of the complex number about the real axis. U is equal to 2 plus I, and v is equal to 1 minus I. We want to find u divided by v. So we proceed in the usual way and write u over v as 2 plus I over 1 minus I. And what we're going to do is we're going to multiply by the conjugate of v divided by the conjugate of v. Notice that this is just 1. And then if we expand this expression, we see that we get 2 times 1 plus I times 1 plus I. And if we expand the denominator, we'll just get 1 times 1 plus I minus I times 1 plus I. Now if we expand all this out, we'll get 2 plus 2I plus I minus 1. And in the denominator, we'll get 1 plus I minus I plus 1. In the denominator, we now have only a real part. So now if we just simplify this expression, we end up with 1 plus 3I over 2. So in the last example, it's natural to ask why we multiplied by the conjugate of the denominator. The main reason is polar coordinates. Let's draw our Argand diagram, and we'll write our complex number as z is equal to a plus ib. Form a triangle where the horizontal length is a and the vertical length is b. The length of this vector is now going to be given by Pythagoras, and we call this length the modulus. Now the modulus itself is not going to determine the complex number because I can have rotations. So I need to determine the angle between the horizontal axis and this complex number. That angle we call the argument. From kindergarten trigonometry, sine is given by opposite over hypotenuse, cosine is given by adjacent over hypotenuse, tan is given by opposite over adjacent. So our kindergarten mathematics says that tan of the argument, or tan theta, is equal to b over a. In other words, theta is given by the inverse tan of b over a. Let's now look at an example of converting a complex number into polar form. In this example, we'll convert z is equal to 1 plus I into polar form. Remember that polar form has two components. We need to calculate its modulus and we need to calculate its argument. So the modulus is just going to be the square root of the real part squared plus the imaginary part squared. So the modulus of z is just going to be given by the square root of 1 squared plus 1 squared. In particular, the modulus of z is just going to be given by the square root of 2. Now recall that to calculate the argument, we need to calculate the inverse tan of the imaginary part divided by the real part. So we'll just get that theta is equal to the inverse tan of 1 divided by 1. In other words, we'll have the inverse tan of 1. The inverse tan of 1 is just going to be pi on 4. The complex number in polar form is mod z e to the I theta. And so inserting the values of the modulus and the argument, we find that z is equal to root 2 e to the I pi on 4. We'll draw our complex number z is equal to a plus bi. And what I can do is I can form the circle which is centered at the origin and has a radius given by the modulus of this complex number. So I want to replace a and b with the modulus and the argument. So what we see here is that the horizontal component is going to be given by mod z times cosine of theta, and the vertical component is going to be given by mod z times sine of theta. So what I can now do is, instead of writing z is equal to a plus bi, so what I can now do is write z as equal to mod z cosine theta plus I mod z sine theta. It turns out that there's a beautiful relation between exponentials and trigonometric functions that is bridged using complex numbers, and that's called Euler's identity. Euler's identity says that e to the I theta is equal to cosine of the argument plus I sine of the argument, so cosine theta plus I sine theta. So what we're going to do is actually give a quick proof of Euler's identity. So if we divide both sides of Euler's identity by e to the I theta, we find that 1 is equal to e to the minus I theta times cosine theta plus I sine theta. Let's define a function f of x is equal to e to the minus ix times cosine x plus I sine x. We need to show is that this is equal to 1 for all x. Now one way we can do this is to just show that the derivative is equal to 0 everywhere, and that initially it's equal to 1. We find that f prime of x is equal to, well, we'll differentiate the first factor and we'll get minus I e to the minus ix, and then we'll leave the second factor alone and have cos x plus I sine x. Now leaving the first factor alone but differentiating the second factor, we have sine x but with a minus sign plus I cosine x. Now if we expand this first term out, we'll have e to the minus ix minus I cosine x minus I squared sine x. Similarly, for the second part, we'll have e to the minus ix minus sine x plus I cosine x, so nothing changes there. So if we combine all this together with e to the minus ix out the front, we'll have minus I cosine x plus sine x minus sine x plus I cosine x. That is equal to 0 everywhere because the cosines cancel and the sines will cancel. So now all we need to do is just show that f of 0 is equal to 1. Plug 0 into this function, we get e to the minus I 0 times cosine of 0 plus I sine of 0. Now Mickey Mouse Maths tells you that cosine of 0 is 1 and sine of 0 is 0. So we have e to the 0 times 1 plus I 0, and the final answer is 1. So that gives us a complete proof of Euler's identity. Since we're now familiar with complex numbers and the conversion to polar form, let's look at graphing of complex numbers. Let's look at z is equal to 1 minus I. We want to analyze this in terms of polar coordinates, so what we'll do is we'll calculate the modulus and the argument. The modulus is going to be given by the square root of 2. The argument is just going to be given by the inverse tan of the imaginary part over the real part. We'll have the inverse tan of minus 1 divided by 1. So the inverse tan of minus 1 is just going to be minus pi on 4. And so the polar form of the complex number is just root 2 times e to the minus I pi on 4. So now visualizing this on an Argand diagram of the complex plane. And so let's say we want to find minus z. So calculating it using the Cartesian form, we have minus z is just minus 1 times 1 minus I. That'll expand to minus 1 plus I. And visualizing that on the Argand diagram. And so what we see here is that it's a rotation anti-clockwise by 180 degrees, and the corresponding polar form here is going to be root 2 e to the I 3 pi on 4. Find I times z. So here, if we do it analytically using the Cartesian form, we'll have I times 1 minus I. If we expand that out, we end up with 1 plus I, and we can visualize that on the Argand diagram. In this case, we see a few things. The argument is now reversed. The main point here, however, is that when we multiply by I, the complex number you get when you multiply by I is a rotation by pi on 2, anti-clockwise. Since we now know Euler's identity, we can use the properties of exponentials to determine properties of complex numbers. So let z equal r e to the I theta and w equal to rho e to the I phi. So r is going to be the modulus of z, rho is going to be the modulus of w, theta is the argument of z, and phi is the argument of w. Now if we multiply these two complex numbers, z times w, which is r e to the I theta, times rho e to the I phi, the moduli will multiply, so we'll just have r times rho, and the exponentials will add. So what we'll have here is r times rho e to the I theta plus phi. The exponential laws tell us that when we multiply two complex numbers, we multiply their moduli and we add their arguments. Now we can do a similar thing with dividing complex numbers. So again, let z equal r e to the I theta and w equal to rho e to the I phi. Then z over w is r e to the I theta divided by rho e to the I phi. So we'll end up with r divided by rho times e to the I theta minus phi. So again, dividing complex numbers divides their moduli and subtracts their arguments. So let's now look through another example, really combining all of these things that we've learnt so far. Let z equal minus root 2 plus I root 6 and w equal 1 plus I. And we'll compute the ratio z over w. Let's just write z over w as minus root 2 plus I root 6 over 1 plus I. As before, we'll multiply by the conjugate of the denominator and divide by the conjugate of the denominator. So now if we expand this out, we end up with minus root 2 times 1 minus I plus I root 6 times 1 minus I. All divided by 1 times 1 minus I plus I times 1 minus I. So if we expand this out and collect the real and imaginary parts, we'll have minus root 2 plus root 6 plus I times root 2 plus root 6 over 1 squared minus I squared. But that's just going to give us minus root 2 plus root 6 over 2 plus I times root 2 plus root 6 over 2. So this time what we'll do is actually use polar form. So again, we have z is equal to minus root 2 plus I root 6 and w is equal to 1 plus I. We want to find z over w. We have already computed their polar forms in previous examples. We have z is equal to 2 root 2 e to the I 5 pi on 3 and w is equal to root 2 e to the I pi on 4. So now z over w is just going to be 2 root 2 e to the I 5 pi on 3 divided by root 2 e to the I pi on 4. So the root 2's are going to cancel, so we'll have 2 e to the I 5 pi on 3 minus pi on 4. So when we simplify this fraction, we'll end up with 2 e to the I 17 pi on 12. Now 17 pi on 12 is larger than pi, so if we wanted it in the principal argument form, we'll need to subtract 2 pi. Now we can write 2 pi as 24 pi on 12, and then this just ends up being minus 7 pi on 12. Hence, in polar form, z over w is just 2 e to the minus I 7 pi on 12. So one thing that's often very confusing is you calculate these complex numbers, you convert them into polar form, and you find that the argument is not what the answer is in the back of the book. That's why we need to make the following remark. So we'll draw a complex plane and we'll only look at complex numbers with the same modulus. Let's consider the complex number z1 is root 2 plus I root 6, z2 is minus root 2 plus I root 6, z3 is minus root 2 minus I root 6, and z4 is root 2 minus I root 6. So all of these you can check have the same modulus, but their arguments will be different. The other thing we need to mention is that there is a convention. Only take arguments that are between minus pi and pi. And so we call this the principal argument. So the negative real axis is going to be the boundary. So let's insert labels for the arguments. The argument of z1 is going to be pi on 3. The argument theta 2 is going to be given by going from pi and then subtracting pi on 3. The argument of z3 is going to be given by going to minus pi and adding pi on 3. And the argument of z4 is just going to be minus pi on 3. So we need to always make sure that the argument lies between minus pi and pi. If you end up with an answer that lies outside of that range, you have to add or subtract some multiple of 2 pi. So one very nice application of complex numbers is that we can use complex numbers to find exact values of trigonometric functions. So we just showed that z over w is equal to 2 e to the minus I 7 pi on 12. And we also showed that z over w was minus root 2 plus root 6 over 2 plus I root 2 plus root 6 over 2. We can go between polar form and Cartesian form using Euler's identity. We'll write 2e to the minus I 7 pi on 12 as 2 cosine minus 7 pi on 12 plus 2i minus 7 pi on 12. So if we then equate the real and imaginary parts of these complex numbers, we'll have 2 cosine of minus 7 pi on 12 is equal to minus root 2 plus root 6 over 2, and 2 sine minus 7 pi on 12 is equal to root 2 plus root 6 over 2. Now, cosine of x is even, meaning that I can just get rid of the minus sign on the inside, and sine x is odd, meaning I can just take the minus sign out the front. And so what we can do is we can write cosine of 7 pi on 12 as minus root 2 plus root 6 divided by 4, and sine 7 pi on 12 as minus root 2 plus root 6 over 4. So let's now take a look at taking the roots of complex numbers. So the first thing we want to look at is solving the equation z squared minus 1 is equal to 0. We get z is equal to plus or minus 1. Gauss's fundamental theorem of algebra then tells us that these are the only roots of this polynomial. If we now visualize these roots on the Argand diagram, we have 2 points on the real axis corresponding to -1 and 1. Now let's suppose instead that we want to look at the cube roots of 1, and what we find is that we actually get 3 points. If we look at the 4 roots, we'll end up with 1, -1, I, and -I. If we look at z to the 5 is equal to 1, then the 5 roots are depicted here. And if we look at the 6 roots of 1, we have this picture. So to actually calculate these roots of the complex numbers and find them on the Argand diagram, we're going to use Demoivre's theorem. So suppose that z to the n is written in polar form as r e to the I theta. Then Demoivre's theorem says that the nth root of this complex number is given by taking the nth root of the modulus. So we're going to take r to the 1 over n, and we'll divide the argument by n. And then since there will be n roots, we need to cycle through. So we'll have this 2k pi over n factor. Let's look at an example. So find the 3 roots of I. So what we'll do is we'll write I in polar form, which we can write I as e to the I pi on 2. Then we want to solve the equation z cubed is equal to e to the I pi on 2. And the kth solution, so we're going to have 3 solutions, z1, z2, z3, denote them generically by zk, is going to be given by e to the I pi on 6 plus 2k pi on 3. So we divide the circle into 3 components. So if we set k equal to 0, we find that z0 is equal to e to the I pi on 6. If we insert k equals 1, we find that z1 is equal to e to the I pi on 6 plus 2 pi on 3. And so if we add these fractions together, pi on 6 plus 2 pi on 3 is going to be 5 pi on 6. So we'll have e to the I 5 pi on 6. And if we take k equals 2, we'll find that z2 is e to the I pi on 6 plus 4 pi on 3. And if we add these fractions together, we'll end up with e to the I 9 pi on 6. 9 pi on 6 simplifies to 3 pi on 2. And so what we need to do is subtract 2 pi. In that case, we see that 3 pi on 2 minus 2 pi is minus pi on 2, and the final answer for z2 is going to be e to the minus I pi on 2. So now if we put these on a complex plane, if you like the video, hit the like button. That'll do some fancy things with the YouTube algorithm to show this video to more people. I'm not going to ask you to hit the bell icon. I never hit the bell icon for anyone, even if I actually look forward to their content. The number of notifications drives me nuts. Be sure to check out the video description, which has notes and plenty of practice problems. If you have any questions, leave them down in the comment section below, and tell me what part of complex numbers do you find most confusing? Do you find that it's just the intuition that's difficult, or maybe it's using Demoivre's theorem? Okay guys, see you in the next video.